I'm Takayoshi Sano. I'll talk about the MRI turbulence with magnetic dissipation. This is outline of my talk. At first, I'll talk about the importance of the resistivity for MRI study, and talk about two different topics. One is a small-scale structure in MRI-driven turbulence, and the second is comparison between viscous MRI and resistive MRI based on the linear analysis and the 2D simulations. The reason why I'm interested in resistivity is to understand the protoplanetary disk evolution, which is very essential for the planet formation theory. Because the ionization is very low, so in protoplanetary disk, resistivity is much larger than viscosity. And many numerical simulation of star formation from the magnetized cloud core suggests that it is quite natural that protoplanetary disk is penetrated by global vertical field. So in many cases, the protoplanetary disk has a net vertical flux. So in that case, accretion stress or MRI activity will be very large. So MRI must be important in protoplanetary disk. But the question is its ionization fraction. And this part will be discussed in the last session of this workshop, the final day, by Mark Warder and Neil Turner. And another important point to include resistivity is that it's good for the study of the saturation mechanism of MRI, because we know the magnetic reconnection plays very important role in the MRI turbulence, and Joule heating, ohmic dissipation, is a dominant term of the thermalization in saturated turbulence. In order to study these terms, we must include the resistivity effect into the simulations. So the importance of the resistivity is characterized by Lundquist number or magnetic Reynolds number for MRI. We define here using VA is alpha speed and angular velocity. Both linear and nonlinear simulations suggesting this number is quite good indicator of the MRI activity. So this is a linear analysis including only resistivity. So black curve is the ideal case. If we put the resistivity, then maximum growth rate decrease largely by the suppression of the dissipation. And also the characteristic wavelengths and also the critical wavelengths decrease also due to the suppression by resistivity. And this figure shows the three-dimensional local sharing box analysis. This shows the saturated stress as a function of this number. As you can see, in order to get a larger saturation amplitude, this number must be larger than unity. So both suggesting the critical number for this Lundquist number is always unity. This is a very good part of this definition. And recently, even in stratified disk simulation, it shows also this Lundquist number is good indicator for the activity of the MRI. But unfortunately, this quantity depends on the saturated field strength, which is very highly unknown in actual accretion disks. So this number is not good for disk modeling. But anyway, so to understand the physical mechanism of the turbulence, this quantity is quite useful. So that's why I use this number in this talk. And saturation amplitude of the MRI is one of the most important quantity what we want to know. And this quantity is depend on basically the field geometry and the resolution. If there is a net vertical flux, then the saturation amplitude is always quite large. So the angular momentum transport by MRI will be sufficient. And also, this is also true for the pure toroidal, net toroidal case too. I'm doing the similar calculation with Charles shows this is a net BY simulation. It's a saturation amplitude as a function of the resolution. So if the BY is relatively large, it's strong, then it results almost converging. But if it's weak, then it decreases with the increase of the resolution, which is quite similar to the zero net flux case. So, but this is preliminary case. But both sets showing that both said the net flux is key for the larger saturation amplitude.
Can you say what's strong and weak?
It's in terms of beta. This is 104 times smaller in this particular case.
When you change the resolution, it's in all three directions?
All three directions. The box size is 1 by 4 by 1, and the resolution from 32 and 64 and 112, 128, using a cubic grid size.
Is the aspect ratio in the radial direction and vertical direction always 1?
1 in this case. Both net by, not net bz, only net by. So anyway, so there's still some resolution dependence. So LP was to perform the higher resolution run. So I perform some relatively large grid number simulation and see the small scale structure in the MRI-driven turbulence. This is a spatial distribution of the azimuthal component of the magnetic field in the slice of the radial and vertical plane. So as you can see, there are many small structures. Model parameter here is, this is a resistive MHD case. The box size here and the resolution is 512 cubes. And the field geometry is a no net flux case in any direction. And the Langkis number is about 30. So the time integration is only 15 orbits. Because in order to avoid the initial linear phase, we put the initial condition of this high resolution case is a copy of the lower resolution case. So, and we consider the structure, the origin of this structure. And what I thought is that this small structure could be a channel flow, which is the axisymmetric MRI mode. And this could be an exact solution of the nonlinear MHD equation. So it goes nonlinear amplitude. And magnetic field is amplified very efficiently through the channel flow growth. And this is the characteristic structure of the channel mode. The channel mode stretches magnetic field line by the motion, horizontal motion in opposite direction. As a result, the magnetic field geometry becomes like this. The arrow shows the toroidal magnetic field is the negative, positive, negative. And the color is a By. So Bx and By is anticorrelated in this mode. And this is a color shows the current density. The channel flow grows, form thin current sheet with the horizontal motion. So we search this kind of structure in this simulation result, and we find lots of similar structure, a channel flow-like structure in this simulation. So here I only marked 12 locations, but I found more than 20. It's just by eyes. I checked.
Identified high current density with candidate channel flux.
Yes. And I checked the structure of By and Bz and Bx at each location. And we look at these two examples, location A and B. So this is an example with a local channel flow growth, I guess. This figure shows the color is a toroidal magnetic field, By. And arrow means a poroidal component in this plane. So the important point is net vertical field is non-zero in this local region. And the size corresponds to this length scale, so which is quite comparable to this structure. And in this case, the net Vz is positive, so poroidal field will bend something like this, and which is correspond to the poroidal field motion and the current structure. This is quite similar structure of the channel flow mode.
The scale of this, what you're showing us now, is about the same size as those small circles that you had on the
Yes,
slide?
exactly. So it's about this size. So this corresponds to the typical MRI wavelengths. So I just choose this size.
So each arrow is pointing from a cell, or is it some sort of interpolation? What is your resolution compared to non-MRI?
The resolution?
What is the size of the
Oh,
grid compared with lambda MRI in that spectrum?
the grid number is 32 by 32 in this region. So each arrow means a grid location. So this is the other example. So again, it shows a quite similar structure of channel flow. This is a B. In this case, net Bz is negative, so magnetic field line bend like this, and due to this radial motion. So it is suggesting that the kind of unit structure of MRI turbines could be the growth and the decay of these small channel modes.
So this simulation is done with a net vertical field or not?
No, zero net flux. Hi.
So what you mean here by the net vertical
In this region,
average of one of those small boxes?
yes, in this region,
On the large scale, the vertical field is
zero. But locally, it exists.
I just wanted to be clear. Superposition.
So actually, the size of this channel flow depends on the resolution. This is we define the two different length scales. One is the MRI wavelength defined by the root mean square of V. And the other is kind of the thickness of the current seed. This shows the color. Red is the MRI length. The green is the current seed thickness. As you can see, as the grid number is increased, then this scale going smaller. Obviously, if the resolution is insufficient, this kind of structure is just defined by the grid size, because it's always about 10 grid size. But we can see some deviation from this line, but it's still not fully converged. So there is resolution dependence, and also there is a initial field geometry dependence. This is a toroidal field distribution in also the XZ plane. This is with net flux and without, so you can see the huge difference in the scale of the channel flow. And this suggesting the channel flow size or unit structure of the turbines could really correlate it to the saturation amplitude. So larger size gives a larger saturation amplitude. So this kind of small structure, or the size of the small structure, could control the saturation amplitude. So this will be very interesting topics. And also, it'll be very interesting to see the single channel flow evolution, including the viscosity and resistivity effect will be very important in nonlinear regime. And I also calculate the energy spectrum of this high resolution lens. This shows we calculate the three-dimensional energy spectrum. This shows along this this figure shows the values on each axis: kz, kx, and ky. So ky power is small means this is an isotropic turbulence. The structure of the eddy elongated toward the y direction, which caused by shear. And this spectrum shows a steep decline at the large k, which due to the dissipation, and which this shows a shallower slope in the smaller k. So in between, there are some specific slope here, and I guess this could be inertia range. I checked this the slope of this range, and by the way, so the MRI in MRI turbulence, By is dominant. So in some sense, the Kz is comparable to K parallel, K pop, and the azimuthal direction could be K parallel. And this is the spectrum in Kz, so which means K parallel. So MRI wavelengths correspond to the K equals 10. So in this region, in this lower K region, the energy input of MRI will be dominant. On the other hand, if we define the dissipation length from this relation, it corresponds to the K equal 50.
These are isothermal,
No,
adiabatic.
adiabatic. But the temperature difference is quite small. It's almost constant, so throughout this simulation.
Sorry to ask it again. These are net field and non-net.
Non-net field.
So that means that in each local region, you're rescaling the lengths according to the local value of vertical field, or?
Here
So
it's
that's the mean of the entire
entire box.
You use that to set the scale.
Yeah. Here I just
Well, the first question of what mean is taken over. Yeah, right. What region that mean is taken over?
so anyway. So if I define these two and if we define inertial range in between these length scale, and we calculate the best fit power here, then it gives minus 3.61, 3.71, which is surprisingly close to the Kolmogorov power.
But that, for the mag, okay, that's the kinetic end, okay.
Yeah, so both kinetic and magnetic shows similar, almost exactly same power.
So is it correct that this power spectrum at low K looks quite a bit different than what Sebastian and Fong with John Takayoshi? Because those were essentially flat.
No, the unique phenomena by this square.
Oh, okay.
So if you compare with what I show some spectra and there will be a K square difference.
So you're dealing with this.
So I compare.
So this is 3D and use 1D spectrum. Okay. So this is the KY direction. So the magnetic and kinetic energy power is shown. And in this case, in the inertial range, we couldn't see any single slope here. But compared to the vertical case, the power is weaker and the steeper, it shows a steeper decline. So these characteristics could be has many similarity to the Goldreich 3D spectrum. So this could be interesting, but I should treat this carefully. So, okay, so this is the second topics. This is a comparison between viscous and resistive MRI. So this dispersion relation is a result just including viscosity, this case. So the same as the resistivity case, the viscosity can suppress the MRI, and the maximum growth rate decrease as the increase of the viscosity. And but the only difference is the critical wavelength is unchanged by viscosity, but the most unstable wavelengths shift longer, as the same as the resistive case. And the growth rate is proportional to the inversely proportional to the square root of the viscosity, which is a little bit smaller dependence than the resistivity. So we consider the difference, origin of this difference. This is a growth rate as a function of the Reynolds number. This the viscous dominant regime, the slope proportion to the this number. So in order to understand these characteristic characteristic quantities, we just do a simple order estimation. So in the if the shear rate is comparable to the viscous rate, then the viscosity can affect the MRI growth. So if we consider the balance between these two frequencies, then it gives this number, which corresponds to the most unstable mode. And the maximum growth rate is the RFM frequency of this length scale. So that's why the maximum growth rate is proportional to the inversely proportional to the square root of the nu. So this is consistent with the linear result. And how about resistive case? Resistive case, if we consider the balance between RFM time and the viscous time, then we can get the same relation consistent to the linear growth rate. So if we know the balance between these numbers, these frequencies, we can guess this characteristic length scale and the time scale just from this balance. So I guess this is very useful. And then we did this simple 2D simulation, just including a viscosity. The 2D means the radial vertical plane and assume the shearing box without gravity. So everything uniform without Keplerian shear. And nonlinear growth, the result said all the model with any size of the resistivity goes to nonlinear growth of the channel mode. This is quite different from the resistive result. This is the amplitude of the nonlinear phase, amplitude of the stress at the nonlinear phase as a function of the Reynolds number or Runke's number. The blue is a resistive case. So if the Runke's number is less than unity, then the amplitude is decreased by many orders. But viscous case, even with very small Reynolds number, the MRI just goes nonlinear evolution. And of course, this is 2D, but the difference is quite obvious. So we consider the origin of this difference. The resistive case, we can understand this result through this diagram. This diagram is a critical wave number as a function of the Runke's number. When the Runke's number is less than unity, the critical wavelength defined by like this. So it inversely proportional to B. And if the Runke's number is larger than unity, then it's proportional to B. So this diagram, this critical wave number, wavelength has minimum at some Longest number is unity. And if initially the Longest number is larger than unity, then as the growth of the MRI, B is amplified, then the characteristic scale is proportional to B. So scale is shift longer, so which means it goes to less dissipative situation. So that's why we couldn't see any suppression in this case. On the other hand, if initially the Longest number is less than unity, then the MRI grows, then the B is amplified and the scale goes smaller, which means it goes more dissipative system. So that's why at some level the resistivity could suppress the MRI. So that's why the critical number in resistive case is unity. How about viscous case? Viscous case, the critical wavelength is unchanged. So it's always VA over omega. So that's why for any viscosity, the system goes to a less dissipative one, and we couldn't see any suppression. Of course, this is just only 2D result, but we just applied this diagram to the double diffusive case, which means including both viscosity and resistivity. This diagram is a critical wavelength as a function of the Longest number. If we fix the resistivity and just put the viscosity, then this line goes something like this. So important thing is that it's always the minimum. So there must be some critical number in Longest number. And this result suggesting that the critical magnetic Reynolds number could depend on the Prandtl number. So, but this is just 2D, so, and it'll be very interesting to see to compare the nonlinear 3D result in future. So this is a summary of this talk, and I just stop here.
So in this picture where you have, a collection of small channel solutions, right? So you did say that the size of this, depends on resolution as far as you can tell, right? So if you keep increasing the resolution, the characteristic size of the small channel solution was going down, is that right? And they start to saturate with high resolution. You show a plot.
The saturation in the small scale.
You show a plot where the characteristic scale of the small channel solutions as a function of resolution.
As a function, so which one? I'm sorry.
It was a plot in which you were showing lambda MRI defined with the local yield field as a function of resolution.
As a function of solution?
Resolution. The resolution of the simulation, the size of the grid. Keep going now.
I just
right? Do you understand why this is happening? Why with higher resolution you will get smaller characteristic scale? Small channel solution?
If the resolution is better, then we can follow the smaller channel solution. So if there are small scale fluctuation, which prevent the larger scale channel flow. So, and the larger scale channel flow is more efficient to grow the magnetic field.
So then why is there a hint of saturation? Because the argument you're giving could be
Dissipation in this case. We put some dissipation effect, so that could, this is with resistivity, so that could make some saturation in a small rate.
Some comments rather than questions. So, one, a bit pedantic. There's a name for that dimensionless combination, dA squared over A1 omega. Sasser number. And this is just a plea to our community to ease communication with people. Maybe we can be a little bit more disciplined about the names we give things. For a long time, we used magnetic Reynolds number. It's something that other people would have considered this number. We just try to be a little more careful and consistent. It helps communication.
But part of this is original definition is a
They
V.
make a substitution for L, so you end up with a quantity which is purely constructed in terms of intensive quantity variables, and should use that.
Sasser, when you have an omega there, it's always the Sasser.
If an agreed upon name already exists, let's use it and roll our own. The other thing I want to make, I really want to congratulate you on this business on channel solutions. I'm not sure that whether or not those are actually channel solutions is something that people argue about, but I think it's certainly a step forward in the sense that you're going beyond second-order statistics in the turbulence, and you're finding coherent structures. We've learned from the hydrodynamic case that coherent structures play a big role. That there are systematic ways of going after such structures involving bispectrum and higher, I don't know too much about it, but it exists. Higher order correlations, and maybe we should start to apply those to some of our simulation data.
Just to follow up on what Jeremy was saying, the fact that having these sort of channel solutions on sort of exponential growth and dissipation fits in what I was saying, because everything may be realized in law normal. So it's nice to see that arrived at independently. The other comment is that it's also well known in the geodynamo community that the L-Sasser number of order unity is typically what is required for dynamo activity. And that's essentially the argument that you were coming to a very different type of direction.
Thank you.
It's that critical number which is dynamos seem to look to seek as they evolve.
Yeah, because like the numerical convergence is an issue. But in 2D, we settle down with the convergence already? It's 3D. It's too confused.
In 2D case, it's not saturated in exactly. I mean, in 2D case, it just go the channel flow. It's just the magnetic field amplitude is increasing still with time
I see. You mean 2D.
in 2D. So it's not saturated value. So that's why we put the arrow in this figure. So up arrow is still going up, and the down arrow is going down. So it's not saturated value. So
Okay, so
Another one is numerical convergence, I think. And I was asking
Oh, yeah.
about
Oh, sorry.
numerical convergence, not about situation.
Right.
Is a different issue.
Oh.
So at a fixed time, are the results converged?
a fixed time. I haven't checked that because it depends on the initial fluctuation. So if we put the same initial fluctuation, it could be the same.
Field calculation.
Yes. To the 2D case, yes.
So you mean the ideal case, there's no saturation?
No, just growing.
Just a quick question about Victor. What are you continuing to it's alpha at the end of the linear state? When
At the nonlinear phase. So after the linear growth, the growth rate decrease with probably strong toroidal field, but it goes increasing, still increasing. We just calculated the last 5 orbit in the end of the calculation. So it's not fair figure. So that's why I don't want to discuss the dependence of this. Just they are not saturated. I just want to say they are not saturated. So
it's the same for the blue cones as well.
yes, it's just in this case they are just going down with time. So
Numerically is okay, right? Given time, so you repeat the question. Follow up. At a given time, increase numerical reasonable.
but this linear growth rate is different. So it's very difficult to fix the time.
You have to adjust.
Yeah.